The next topic in mathematics is series. And here we'll look at arithmetic and geometric progressions, and then Taylor and Maclaurin series. So first of all, progressions and series. An arithmetic progression is a series of numbers in which there is a constant difference or addition between the terms. And here are the definitions as given in the reference handbook. So here the last term is A, the difference between the numbers is D, the number of terms is N, and the last term is L. So the relevant equations are given here. The last term is the first term plus number of terms minus 1 multiplied by the difference, or conversely, the number of terms is given by this expression. And the summation of the series S is given by either this expression, n a plus 1 over 2, or equivalently, n multiplied by 2a plus n minus 1d over 2. A geometric progression is a sequence of numbers which increases each term by a constant multiple that we denote by r. So here again are the relevant equations from the handbook. So the first term is a, the common ratio or the multiplicative factor between the terms is r. So the last term L is given by the first term multiplied by r, the ratio multiplied by the raised to the power of n minus 1, and the summation of the series, the sum of the series, is equal to a minus rl over 1 minus r, or equivalently a times 1 minus r to the n divided by 1 minus r. Some properties of series are given. For this example, the summation of a series in which each number is a constant equal to c is just equal to the number of terms multiplied by the constant, and the summation of a series which is all multiplied by a constant value c is equal to c multiplied by the summation of that series. The summation of individual series, summation of xi plus yi minus, for example, zi, you just add or subtract the summations of the individual series, etc. And a power series, whose formula is given here, is equal to the summation from I equals 0 to infinity ai x minus a raised to the power I, where I is an integer. And a special case of this is where the constant a in the parenthesis is 0 is equal to the summation from I equals 1 to infinity ai x to the I minus 1 is given by this expression here. And finally, another expansion which we'll use is the Taylor series, which is useful for expanding the value of a function about a point, is given by f of x is function of a plus f prime of a over 1 factorial x minus a, etc. And we'll show you an example of that in a minute. So some examples of this. First of all, we have a finite sequence of numbers, 15, 19, 23, 27, etc., up to 59. And the question is, the sum of this series is which of these alternatives? So in this case, we see that by inspection, it's an arithmetic series increasing by 4. In other words, each successive number is 4 bigger than the one before it. And we also see that the value of the first term in the sequence A is 15, the last term is 59, and the difference D is 4. So we can use the formula, for example, in this form. The summation is equal to n times a plus l over 2. But we don't yet know how many terms there are in that sequence. You could probably do it by inspection, but let's calculate it. From this formula, that the last term, L, is a plus the number of terms minus 1 multiplied by the difference, or rearranging, the number of terms is L minus a over d plus 1. So plugging in, last term is 59, first is 15, difference is 4, so therefore there are 12 terms in this series. And now we can go back to our summation formula and evaluate that. So S is equal to n, a plus l, which is now equal to 12 times first term plus last term divided by 2 is equal to 444. So the answer is D. The next example, we have a finite sequence of numbers, 20, 30, 45, etc., up to 227.8. The sum of this series is which of these alternatives? So here we see by inspection that this is a geometric series where each term increases by a multiplicative factor of 1.5 compared to the preceding term. And we see that by inspection the values of the variables are the first term A is 20, the last term L is 227.8, and the multiplicative factor R is 1.5. So we can use the summation equation in this form. S is equal to A minus RL over 1 minus R. We know all the terms in that equation is equal to, therefore, 20 minus 1.5 times the last term, 227.8, divided by 1 minus 1.5, and the answer is 643.4. So the closest answer is C. And you can also show, either by inspection if you like, that there are 7 terms here, n is equal to 7, and just convince yourselves that the last term is indeed given by this expression, L is equal to AR to the n minus 1. Now we'll finish with an example on the Taylor series, and we want to form a Taylor series of the function f of x equals exponential, or e to the 2x, about the origin, about a equals 0, to estimate the value of the function at a point B which is close to a. And the question is, what are the first 2 terms in the expansion about x equals 0? Which of these alternatives? So here is the section again from the reference handbook, and here is the formula for the Taylor series. F of x is equal to a function evaluated at a plus the first derivative, f prime evaluated at a, divided by 1 factorial times x minus a, plus the second derivative, f double prime evaluated at a, divided by 2 factorial, multiplied by x minus a squared, etc. But here we're asked only for the first 2 terms, so we just want to evaluate these terms in the expansion. So to do that, first of all, we evaluate function at a, where a is equal to 0. So e to the 2x evaluated at x equals 0 is equal to e to the 0, which is 1. The derivative f prime of x is 2e to the 2x. So the derivative evaluated at x equals 0 is equal to 2e to the 0, which is equal to 2. So then we can evaluate these 2 first terms here is equal to f of a plus f prime of a over 1, etc., is therefore equal to f of a is equal to 1, f prime of x is equal to 2 divided by 1 factorial, and multiplied, and a is equal to 0. So the first terms are 1 plus 2b, and the answer is B. Now, let's just look at what we did here. Here is a graph of the function e to the 2x. It looks like this. And what we're doing is finding the Taylor series about this point 1 so that we can evaluate the function at some other point, say here. So in this case, we're only evaluating the first 2 terms. So in other words, the value of the function at some nearby place here is equal to, we just take the slope, the value at this point here is equal to the value here, which is f of a, plus the derivative f prime of a, which is the slope of this line, multiplied by the horizontal distance from here to here. And that's what the first 2 terms are. And from this you can see, obviously, that this is only a good expansion for points which are very close to the original point. So the first 2 terms are only good for evaluating functions which are very close. If we wanted to evaluate the function very far away, then linearizing this would then become a very poor approximation, and we would have to take more terms in the expansion. So this completes our discussion of series.